Breaking news. At 0136 UTC today, automated alert systems lit up simultaneously across space agencies on 3 continents. Data streams from orbiting telescopes and ground-based arrays began flashing red within seconds. In control rooms in Pasadena, Darmstadt, and northern Chile, scientists watched the same impossible pattern unfold in real time. Today, the impossible just happened. Moments ago, NASA confirmed that archival data from the Transiting Exoplanet Survey satellite, TESS, revealed a 28-hour gap in publicly released footage of the interstellar object known as 3I Atlas. Within that missing window, something occurred that no current model of astrophysics can explain. This changes everything we thought we knew. If you want real-time updates on the most mysterious discoveries in the universe, hit like, subscribe, and stay with us, because what you're about to hear is not speculation. It is data, and it is unprecedented. The confirmation did not come from a single analyst or a lone telescope. It arrived as a convergence of independent systems, each validating the same anomaly. NASA's Deep Space Network detected an unexplained fluctuation in telemetry timing. Minutes later, ESA's European Space Network flagged an irregularity in archived tracking logs. Almost simultaneously, optical observatories in Chile reported brightness curves that did not match any version of the official release. At Harvard's Center for Astrophysics, graduate researchers were instructed to halt simulations mid-run. At Caltech's Jet Propulsion Laboratory, senior scientists were called into emergency briefings before sunrise. The James Webb Space Telescope was quietly retasked to observe the outbound trajectory of 3I Atlas in near-infrared bands between 0.8 and 5 microns. Hubble followed, cross-checking visible light albedo changes. At the Atacama Large Millimeter Array, technicians pivoted multiple dishes toward the object's predicted coordinates. This was not a software glitch. This was consensus. TESS, operating from its high Earth orbit, had captured continuous photometric data on 3I Atlas as it crossed a region of space roughly 1.4 astronomical units from Earth. That dataset, normally released in routine batches, contained a discontinuity. 28 hours of footage were missing from the public archive. At first, it was assumed to be a processing delay, but when internal timestamps were compared with external tracking data, the discrepancy became undeniable. Something had been removed. 48 hours before the event, everything appeared normal. Orbital elements showed a clean hyperbolic trajectory, confirming the object's interstellar origin. Velocity relative to the Sun was measured at approximately 41.7 kilometers per second. Surface temperature models placed it near 140 Kelvin, cold and inert, with no visible coma and no detectable jets. Spectroscopy revealed a composition consistent with carbonaceous material mixed with water ice and trace silicates. Nothing exotic, nothing alarming. 11 hours later, subtle anomalies began to appear. Tracking stations in Goldstone detected a micro-deviation in acceleration, just 0.02 millimeters per second squared. Insignificant on its own, but when Madrid and Canberra confirmed the same perturbation, analysts took notice. There was no corresponding outgassing force. Solar radiation pressure could not account for it. 6 hours after that, thermal maps from Atacama showed uneven heating across the surface of 3I Atlas. Instead of a smooth gradient, the object displayed segmented temperature zones, fluctuating by up to 35 Kelvin over intervals of minutes. No known passive process could produce such controlled thermal variance in deep space. Then, 2 hours before the TESS blackout window began, rotational data revealed a sudden stabilization. 3I Atlas had been tumbling chaotically since discovery, Now, abruptly, its rotation aligned along a single axis. Angular momentum appeared to dissipate without a corresponding energy loss. That was the first red flag. At 1912 UTC, TESS began its high-cadence observation pass. For the next several hours, photometric readings showed a steady light curve, punctuated by faint oscillations in the ultraviolet band near 210 nanometers. Then, at 2347 UTC, the signal changed. Brightness increased by 4.3% in less than 90 seconds. Simultaneously, TESS recorded a transient spectral feature centered at 1.6 microns, an emission line not associated with any known cometary process. And then, abruptly, the public data stream ended. For 28 hours, TESS continued to observe 3I Atlas, but that footage never reached the open archive. What happened during that window is now the subject of intense investigation. Internal logs, later corroborated by ESA telemetry mirrors, show that during the blackout period, 3I Atlas underwent a rapid morphological change. High-resolution reconstructions suggest a reduction in its major axis by approximately 11%, accompanied by a lateral expansion that preserved total volume. In other words, the object changed shape, not through fragmentation, not through sublimation, through reconfiguration. No natural process could produce such symmetry on that timescale. When the public feed resumed, 3I Atlas appeared subtly different. Its aspect ratio had shifted, its surface reflectivity had increased, and its thermal signature had become unusually uniform. Within minutes, emergency calls were made. Dr. Elaine Porter at ESA initiated a cross-agency verification protocol. Dr. Jonathan Reyes at Caltech ordered immediate N-body simulations to test whether tidal forces or solar radiation pressure could be responsible. They were not. 3 hours after the data stream returned, ultraviolet spectroscopy detected repeating emissions at hydrogen Lyman alpha, 121.6 nanometers, pulsing at precise intervals of 19.7 minutes. Radio arrays soon followed, registering faint broadband oscillations between 1.4 and 1.6 gigahertz. Not narrowband, not a message, but structured. Pulse intervals began to shift. 19.7 minutes, then 11 minutes, then 7 minutes. Prime number spacing. This was no longer random. This was responding. At MIT, gravitational modeling ruled out internal collapse. At the Max Planck Institute, material physicists confirmed that no known ice-rock composite could rearrange itself without catastrophic fracture. At Stanford, machine learning classifiers trained on millions of cometary and asteroidal events returned a null result. There was no precedent. Two hypotheses emerged. The first, the mainstream explanation, proposed that 3I Atlas might be composed of an exotic, metastable interstellar material capable of phase transitions under minimal energy input. Proponents pointed to unknown chemistry, to physics yet undiscovered, to the vast diversity of environments beyond our solar system. But the second hypothesis was more unsettling. It suggested that the object was not passive, that the observed changes were controlled, intentional, technological, or governed by physics far beyond our current framework. Dr. Marcus Hale of Harvard reportedly stated in a closed briefing, if this were occurring in a laboratory, we would classify it as active matter. Then came the second wave. 17 hours after the TESS blackout ended, one surface feature, previously identified as a minor protrusion, simply vanished. Not detached, not eroded, it disappeared across optical, infrared, and radar wavelengths simultaneously. No debris, no plume, no energy spike. The remaining structure adjusted within minutes, redistributing mass to maintain balance. At the same time, magnetometers aboard low Earth orbit satellites registered a localized disturbance, approximately 0.3 nanoteslas, synchronized precisely with the pulse interval from 3I Atlas. Minor, harmless, but unprecedented. Inside mission control rooms, the atmosphere shifted from curiosity to silence. Encrypted communications increased, data access was restricted, analysts noticed delays in public releases. World governments were briefed, not on conclusions, but on uncertainty. Subtle effects followed. A cluster of communication satellites experienced transient dropouts. Radio blackouts flickered over the South Pacific. Navigation systems reported timing errors measured in nanoseconds. Even wildlife researchers noted slight deviations in migratory bird paths coinciding with brief geomagnetic anomalies. No one announced panic, but no one dismissed it either. As days passed, emissions from 3I Atlas began to stabilize. Pulses aligned, thermal output converged toward equilibrium. Surface geometry settled into a smooth, faceted configuration exhibiting rotational symmetry to within 0.01%. It was no longer behaving like debris, it was behaving like a system. I remember staring at the data feed as the latest update arrived before dawn. The graphs were calm, the equations balanced, and yet nothing about them felt reassuring. Because for the first time, we were not just observing an object behaving strangely, we were witnessing behavior. In quiet moments between briefings, reflection replaced urgency. For centuries, we believed the universe was indifferent, a vast arena of matter and energy following immutable laws. But what if some of those laws include agency? What if intelligence in some form is not rare, but simply subtle? Maybe we're not witnessing the end of certainty. Maybe we're witnessing an invitation. As 3I Atlas continues its silent passage through our solar system, instruments remain locked on target. Every pulse is logged, every fluctuation analyzed, every deviation from expectation cataloged. The lost test footage remains classified. The questions continue to grow, and one thought refuses to fade. What happened during those 28 hours, and what happens when it changes again? Subscribe to follow the next update, because the story of 3I Atlas is far from over.